Hi, everybody. This is Matthew Poes with Poes Acoustics. And in this episode, I got my good friend Mike Raley from Pack International. Mike, you want to introduce yourself?
Yeah, so I am with Pack International, and thanks for having me on here. It's great to be able to come chat with you about sound isolation. So I am Pack's director of engineering. Pack is a manufacturer of noise control products, sound isolation products, which I'm sure we'll kind of get into, what that is and all of that in this conversation. Um, my background is in acoustics. I have a bachelor's in acoustical engineering from Purdue University. I worked as an acoustical consultant for 10 years, and I worked on apartment buildings and hospitals and recording studios and listening rooms and performing arts venues and all kinds of different stuff. I also did environmental noise stuff where I'd go out and do measurements in places like my background here. And now for the past like 7 years or so, I've been working as an acoustician engineer for product manufacturers, and do a lot with acoustical testing and product development and standards development and all this kind of stuff.
Yeah. So thanks for coming on. I think I've known you now for, I don't know, a year or two,
Hmm.
at least a year,
Yeah,
where I
I
had
think
joined
so.
one of your webinars for Pack, and it was a very interesting webinar. And then you and I got to chatting afterwards. I think we had some phone calls and emails, and I've just
Hmm.
found you to be a very helpful person because there's not that many people. It's a relatively small industry. Like I feel like once you meet somebody in the industry, they know all the other people that you know, kind of
Oh
thing. I
yeah.
actually was talking to somebody recently who brought you up at one of the labs that we're using for some testing, and
Oh,
so
okay.
a bit of a small world. And
Very much so.
I think you referred to you as part of the new young group that's coming in and actually doing new. Like he was kind of saying, like the old timers, they have a lot of experience, but they don't necessarily feel comfortable trying new things. The new young people coming in maybe don't have the experience, but they're also more open to new things. And there's a lot of stuff that, especially in the United States, we do that are like not the right way to do it, but they never bothered to update the standard. And so thankfully, new
Yeah,
young people are coming in to fix that.
I would happily lump myself into that group of the new young people, although these days I'm not feeling quite so young anymore. But yeah, some of the younger crop of folks coming in and trying to kind of change things and stir things up a bit and bring acoustical testing into at least the latter part of the 20th century, ideally someday
Yeah.
into the 21st century. But
It is one of my preferred methods for sound isolation testing. I think when it first came out was adopted in Europe, it was referred to as the new method. I believe it's about 20, 25 years old though. And it still has
yeah,
not been adopted in the US because it uses a swept sign.
well, we can get into that, but the swept sign method, at least for reverberation measurements, sound absorption measurements, um, is currently going through the balloting process at ASTM right now, and I don't think it's actually been fully approved yet, but it's in process and hopefully will be approved soon. We won't use that for transmission loss measurements yet, but we'll at least use it for figuring out decay rates.
Yep,
So
which is
we are
great.
making
I mean,
progress.
it has so many advantages that it's kind of shocking they've never bothered. I like it for sound isolation. We can get into some more interesting topics on this, but I like it because the signal to noise ratio of the swept signs is so much higher than like pink noise or white
Oh
noise.
yeah, of course.
Right. It's yes. And when you're out in the field and you're testing, you have a couple problems. So one is you have no way to control the noise floor of the receiver room. So you've got the source room where you're making all the noise. I can kind of control that, but I'm still limited by whatever speaker I either A brought or B is in that room already.
Yep.
And if it's a client system, I don't want to break their speakers trying to play it loud enough to overcome the
Reas-
noise on the other side in the receiver room.
Reasonable. Yep.
Right. And then in the receiver side, it's like, I don't know what that's going to be. Is it going to be just like some sort of anteroom? Is it going to be like a kitchen? I mean, I actually had one once where the theater opened up into the living room kitchen.
Yeah.
And during the time, because this is all I was allowed to do during the time that I was working, since they were running 3 shifts, the theater was mine. Everything outside the theater was the contractors. And I had to do isolation testing with contractors working on the other side. Like the most I could get them to do is be quiet for 5 minutes so I could run a sweep.
Yeah.
Pink noise would have been a tough measurement in that environment.
It would have been an awful measurement. Yeah. And I mean, even in the laboratory environment, right? Like where it is a controlled space, a highly controlled space, and we try to design our, receiving rooms, especially in the lab where we have much lower noise floors and things like that. when I'm going in and I'm doing testing, I like to try and build really high performance things. I have a habit of going in and like kind of pushing the boundaries and kind of breaking labs and finding issues and things like that. So we're often bumping up against the noise floor, especially at higher frequencies where we've got really high TL values.
Yeah,
And
over
so
100 dB often.
yeah, and so in those cases, right, like um still having that better signal noise ratio where you can just cram all of that acoustic energy into this really narrow bandwidth, like that gives huge benefits.
Yeah.
So
It
yeah.
makes perfect sense, and I can't wait to see that get adopted. Well, anyway, I brought you on here. So the reason I wanted to have you on here is that, again, we can talk about all these fairly complicated and advanced topics of isolation, but the reality is many people in my audience are really more at the basics of like, what is sound isolation? I just had this conversation with somebody recently who wanted me to put something together for them as part of a proposal, and they made a comment that's actually very true. I hear it all the time. It's really common that people conflate sound isolation with acoustical like treatments, or so
Yep.
that one of them is dealing with the reflected sound in the room and how we manage that, and the other has to do with sound getting through the walls. And when you say like, I'm an acoustical engineer, I do sound isolation, they're like, right, you put a bunch of foam on the wall. And it's like, no, that actually does
Yep.
almost nothing.
Yep.
um,
Yeah.
so why don't you talk a little bit about the differences between those, and basically the core maybe physics principles that we're dealing with when we're trying to create an isolation wall?
Yeah. So that's a great question. It's something that I run into a lot, and it's a sort of a misunderstanding or a fuzzy understanding that I find from a lot of folks. I mean, people who are just kind of trying to figure out acoustics because they're trying to build a home theater or home recording studio, but I also get it a lot from like architects and things like that too, who have dealt with acoustics a lot more. So rather than like going into a bunch of acoustics jargon and things like that, I like to try and use analogies to kind of help people understand things. And one I've been thinking about recently for just this particular question, and I'm curious kind of how this lands with you, is that if you're thinking about like controlling noise, or sound in a space, we can think about it like water, right? So if you're trying to control water in a space, right? Like say you have some water that's spilled into your room, right? You've got water on the floor, right? And you want to like soak that water up, right? What do you use to soak up that water?
Like a towel.
You'll use a towel or something like that, right? So
Yeah.
something that's kind of soft and fuzzy, right? And absorptive, right? That will absorb the water. So when we're talking about room acoustics, we've got sound moving around in the room, just like water moving around in our room or in this container, right? And we want to absorb that sound, right? We want to kind of soak it up, right? And so we'll use soft things like the panels, it looks like behind you right there, that will kind of absorb that sound, right? And so that reduces the amount of sort of sound that's sloshing around in our container, right? It absorbs it. But on the other hand, if we have water and we want to contain that water so it doesn't spill out and go all over the place in the room, I imagine that most people would not use a towel to hold water. You wouldn't say, oh, here, hold this towel and let me pour some water into it and we'll hold it that way, right? And it's the same kind of thing for sound, right? If we want to contain sound within a space or keep it from going from one space to the other, we need a container that will help hold that sound in. And so just like with water, we use some hard, rigid container, a glass bowl, or something like that, right? To contain sound within a space, we want to use some hard, rigid container. And so that's where we get into, drywall walls or, concrete walls, CMU block, all these kinds of things, hard, rigid things. Now, there's a lot more to it than that. But I think that kind of analogy sort of helps, like it's controlling the sound in the space, absorbing the sound. We need a towel. If you're trying to keep it in one space and contain it, we need a solid container.
Yeah, I think that's actually a good analogy that helps to explain the concepts. I could see some people misunderstanding that to an extent that they take it in the wrong direction, but I think that this is one of those issues. Sometimes we have to simplify things to the extent that they're technically wrong to people who know what they're doing, but to the average 97%, it's the best way to easily understand the core concept. So I think this falls into that of like, that is a really good analogy for explaining how we're absorbing sound versus blocking sound. I think that so the next question I had for you. Well, you looked like you had something to say, so I'll let you say what you're going to say, and then I have another question that relates to this.
Yeah, I was just going to say, I like your point that, like, yeah, this is an analogy that at a basic level just kind of helps understand the basic concepts, but like we don't want to over extrapolate from some sort of analogy and think that
Yep.
like this analogy of the towel or the container really helps us actually understand the physics of how sound behaves in a space or transmits from one space to another, which I'm sure we'll kind of get into as you ask more questions.
Yeah, for sure. So one of the things so somebody asked me a question the other day, and this is somebody who actually I think knows enough about what they're doing that they probably didn't mean it this way, but it's a question that I've heard asked in a way where it's a common misunderstanding. So in sound isolation, we typically are dealing with mass, and I think mass is the one everybody knows. It's like the one, in fact, I think it's like over considered, if you will. They're like, yeah, just make the wall more massive. And it's like, well, there's some other things to consider first, because there's a limit to just how massive we can make these walls.
Yep.
So you got mass, you have decoupling. So, basically stopping, we'll call it the inner structure from passing vibrations and sound waves through to the outer structure. You've got resonant frequencies, and we have two primary areas those show up. You've got the actual materials that you're putting on the wall that have their own, the coincident frequency, and then you've got the mass resonant frequency, which is the cavity resonance, from having multiple, like usually you have an inner wall and an outer wall, even if it's just a 2x4 wall. And then you've got what I call the pressure zone, the area below that's primarily controlled by stiffness. And that's really low frequency stuff that isn't even measured in labs, but at least in the physics side of things, it's a theoretical part of it that we got to deal with. So
you can actually see that stiffness zone show up in lab test data.
Do you?
Oh yeah. But we can get into that, and I can kind of we can go through some things too.
So the thing that gets me is, so somebody will say something like, how massive are the walls you build? And then you'll tell them, they're like, oh, well, my walls are twice as massive. And it's like, well, that doesn't tell you very much, because there's more to isolation than just mass. And in fact, it gets to a point where you got to double your mass to get 6 dB more isolation. And it gets to a point where, like, what that actually means is a very significant increase in mass, and including at some point the wall will fall down. Like, it's not going to support its own weight. And so you have to look for other ways to isolate. And actually, it's one of the first things I do, and that's the decoupling. So when you gave your analogy, I was imagining a bucket, and I was thinking, like, this is where things get a little goofy. Like, if you fill water in a bucket, that water is not coming out of that bucket if it's a fully sealed bucket, no matter what.
Yeah. Right.
And so if you stick it in another bucket, that doesn't do you any good. It's still not passing any water through.
Yeah.
But where you run into something that I think is a similar analogy would be if you take a bucket and you put, instead of putting water in it, you put I actually had a weird word, and I'm like, no, I'm not going to use that one. That's going to give the wrong illusion. So if you were to put like an electric sander in it, because it vibrates, you put like an electric sander in there, right? And you don't want to feel those vibrations through the bucket. You could make the bucket out of like solid concrete. And if you made it big enough, you probably wouldn't feel the sander's vibrations through it. But it would have to be really, really, really massive. And it would be very hard, to the point that it may not even actually work. You may always feel those vibrations trans through, because concrete can still conduct vibrations and actually sound waves pretty well.
Totally. Yeah.
So the other thing you could do is you could take this bucket, and it could still be a lightweight plastic bucket, and you could stick it inside of another bucket and float it such that it doesn't touch the other bucket. And at that point, you probably wouldn't feel those vibrations in the outer bucket at all. And that's kind of the concept, in my mind, at least, of why we do decoupling, because it allows us to keep the sound energy hitting the one wall from passing through to the other wall. It's more of a conduction process, but it's pretty effective.
Yeah, right. Yeah, and I think, like, as we start to talk about like actual sound isolation and like how, we use a wall or some other sort of structure to reduce the amount of sound that goes from one space to the other, it's helpful to think more about, again, still at a basic level, how the sound actually gets transmitted from one side to the other. So like, sound at its most basic is just pressure fluctuations in the air, right? That's what we hear, right? So it's these pressure fluctuations. So you have, air particles that are being squeezed together and then coming apart, right? And the sort of the analogy or picture that's often used for it is like, if you have a slinky that's stretched out, and you flick one end of the slinky, and you have this kind of wave, right, that propagates across the slinky, right? That's the same kind of way that sound propagates through the air. So if you have these sound waves, it's these kind of pressure fluctuations or these air particles kind of moving back and forth. So when those air particles hit a surface, like the drywall of a wall, right, those pressure fluctuations will push that drywall and make it move back and forth. And then whatever that is connected to will also move back and forth. And then, you'll get the drywall on the other side of your wall that's moving back and forth. And then that will make the air on that side of the wall move back and forth. And then that's what you hear on the other side of the wall, right? So you have all of these kind of different steps. Well, so as you increase the mass, right, you increase the mass that has to be moved back and forth, right? And so for
Yeah,
the same
the
amount of
inertial energy.
energy, right. So you have higher inertia. And so for the same amount of energy, you get less movement the higher the mass is, right? It's just like, trying to push, the difference between me trying to push my kid in their little, Hot Wheels like ride-on kind of car thing versus like me trying to push my Honda Accord, right? Like I'm
Mhm.
pushing the same amount, but like if I push the car with the little kid in it, like it's going to go really far pretty fast, right? But if I try and push my Honda Accord, it's not going very far or very fast at all, right? Um, so same thing kind of thing, right? We increase the mass of our walls for the same sound energy hitting it, it's just moving less. And so then the air on the other side moves less. But also if we can, decouple it when this side's moving, right? Less energy gets transmitted to the other side and it moves less.
Yeah, kind of like if you cut that car in half and attach the two pieces together with springs, you
Yeah,
would have to compress the springs before the other side would move.
yeah, exactly, right? Yeah, or it's just like, if you have something that's got some give in it and you're trying to push it, right? You
Yeah,
have to push through all of that give first before you
before it
actually
can.
get it to
Yeah,
actually move or something like that.
and
Yeah.
so one thing I'll say, even I get caught up with this. Like sometimes I'll be trying to think of better ways to isolate walls, and I'll find myself compounding isolators, or trying to effectively do that. Maybe not literally, but like one thing I think I think I asked you about this once, had to do with like, well, what if don't I want like a lower gauge hat channel with less clips, for instance, which are so that's one of the methods we use for decoupling. Is you've got these clips, they have little rubber grommets on them, they screw into your studs, then attached to that is hat channel. The typical that we use is 20 or 22 gauge, but you can use 24 gauge. And so the thought was like, well, wouldn't that be better because it's more resilient? And so I think what I get caught up in sometimes is like, you you can essentially have complete decoupling or close enough to complete decoupling that trying to add more is actually creating more problems than benefit. Is that, am I capturing it right?
Yeah, yeah. And there's a couple different aspects to that. So one is that if we have sort of multiple isolators in series, right? So you can imagine like you've got a trampoline, right? So that's this sort of isolator, right? Like, you're moving on it, bouncing up and down. It flexes, but like your impact doesn't get transmitted to the ground underneath, for instance, right?
Right.
But then imagine you have a spring, right? Just like a big steel spring, which would be another isolator, right? And you put that on top of the trampoline, right? So if you have a stiff steel spring, like say from your car suspension, right? And you put that on the trampoline and you push down on the steel spring's not going to deflect at all. Just the trampoline's going to give, and you'll get nothing out of the steel spring until you've bottomed out the trampoline, and then you start compressing the spring, right? But if you have a spring that's of the same sort of stiffness as the trampoline, they're both going to kind of compress as you push down on them, right? And so one of the things that we run into is if we have, you know, two different kinds of isolators, well, how stiff are they and how stiff are they relative to each other? And this comes into play, when we're looking at putting isolators onto a floor to do something like a floating floor or something like that, which might
Mm-hmm.
be common for a theater or recording studio.
Sure. Keep noise
So
down.
when we look at, the isolation efficiency that's going to come from an isolator or something like that, the standard assumption that's built into that is that it is on a rigidly, an infinitely rigid
Surface.
structure
Yeah.
surface, right? Um, but in the real world, we don't have infinitely stiff structures. And, if we're talking about a single family residence and somebody's doing a home theater or something like that, and, a second floor room above their garage or something like that, it's nowhere near infinitely stiff. It's a pretty floppy structure. And so if we put some
Sure.
isolators on it, like the isolators, it might be like that spring on the trampoline where the floor is, deflecting just as much or more than the isolator is. And so the effectiveness of your isolator is less. So there's that kind of interplay So sometimes having a really stiff structure and then putting a really soft isolator on that stiff structure can be advantageous. But then also the other kind of aspect to this is sort of diminishing returns, which I think you kind of got to at the beginning, which is, if we think about a a typical stud wall, and it's maybe less diminishing returns, but also kind of thinking about where the sound is going through, how the sound is actually passing through that wall, right? So if you have a typical, just say a wood stud wall, right, where you have, your studs at every 16 inches, for instance, right, and then you have some insulation in the cavity between those and drywall on either side. So one of the first things we will do to kind of improve the sound isolation of that wall is we'll create some decoupling, right? So we'll, at least on one side of the wall, we'll use something to isolate the drywall from the studs. And that might be Brazilian channel. That's like the cheap basic version of it, but it's got its issues. Or you might use clips and hat channel, which is, something that Pack manufacturers, Pack created the first clip. And there's, a bunch of different options for that and things like that. So you'll have these little clips, like you said, with the little rubber isolator in them, and then you'll put hat channel in those and attach your drywall to that. So that isolates this structural path, right? So you've got the drywall that's vibrating, and then it's on the hat channel, so then the hat channel vibrates, and then that's on this clip that's on this rubber isolator. But the rubber isolator kind of allows the clip to vibrate independently of the stud that it's attached to. So you've isolated the structural transmission path. But you still have another transmission path. You've got the drywall between the two studs. That drywall is vibrating, and it's vibrating the air inside that stud cavity, which then vibrates the drywall on the other side and keeps going through. And your isolation between the drywall and the studs doesn't really affect that sort of cavity path. And so if you've isolated your structural path enough where it's no longer contributing that much sound energy that's going through, then your cavity path becomes dominant, and further isolation of your structural path doesn't do anything other than just take more money out of your pocketbook.
Right. Yeah. So basically, you have to be balancing all of these different factors. At some point, you've got it like you. So I think what you said is kind of how I approach it. The first thing you want to do is decoupling. I look at that as your biggest initial bang for your buck. So if you take, I mean, you can probably apply some numbers to this a little better than I can, but if you take a standard 2x4 wall with 1/2-inch lightweight drywall and no insulation, I'm guessing you're going to be like STC 20 to 25, something like that. A little better.
I don't even know, because I don't play in that world, so I have no idea.
Well,
so like, so I will say that, like, I think a typical 5/8 Type X drywall to 2x4 wood studs with insulation in the cavity is probably going to be in the mid-30s STC range. Like 36 is kind of what I have in my head, something like that. So
with
insulation drywall
insulation?
with insulation. But again, when your drywall is attached rigidly to your studs, your structural path is going to dominate. And so if you test that wall with or without insulation, there's actually not a huge difference. So with lightweight 1/2-inch drywall, maybe high 20s, something like that.
Yeah. Okay. So we'll go with your numbers in high 20s, and then you move up to a stiffer drywall. Not stiff. Well, it is stiffer, but you move up to a denser drywall.
A heavier, higher density, heavier drywall. Yeah.
You're going to get a little bit more, a couple of points out of that. Add some insulation. That's going to deal with the cavity sound that's passing through to some extent. But like if you add in a decoupler, like the Pack clip with hat channel, and you keep the 5/8 Type X drywall, you don't add extra layers, you just leave it as is with the insulation. If I recall, it's a good 10 to 15 point increase. It's pretty solid, right? It goes from, call it,
it's like,
35 to like
20. So
20. Okay, so it's more than I'm saying. Yeah, I couldn't remember just how big it is, but it's a big jump. It's like, and the thing is, remember we said earlier, for those watching, you have to double the mass to get 6 points. So if we were to take and add 2 extra layers of drywall to both sides of that wall, we'd only get 6 extra points of isolation. If we add these clips and hat channel, which is probably on par or only slightly more expensive than the extra 2 layers of drywall, we've actually gained 20 points. It's a much bigger boost.
Yeah, so I just pulled it up. That's why I was looking over to the other side for a minute. So one of my standard references for test data for just like basic walls like this, which is 2x4 wood studs and drywall and things like that, it's it's relatively old data. It's about 30 years old at this point, but it's a great place where they've tested tons of different versions, and it's all kind of back to back, which in the same lab, which reduces variability, which maybe we can have that conversation another time.
Don't
But
scare
so
my
this
audience. They think the lab data is solid and we should trust it unequivocally.
okay, well, we'll definitely have that conversation another time then. So this is the National Research Council of Canada. So this is a government acoustics test lab in Canada. Great lab, does a ton of research and all this kind of stuff. So this is one of their reports. So this is half-inch drywall. This is still Type X, so it's not the regular lighter weight drywall, but this is a half-inch Type X this is actually with mineral fiber insulation in it, which we can talk about mineral fiber versus fiberglass at some point. But this is an STC 34. 5/8 Type X on the same wall, also with mineral fiber, is also an STC 34. And that's just direct attached. 2 layers of drywall, 2 layers of half-inch Type X on both sides is an STC 38. So we didn't quite get the 6 points for doubling the mass, but we're close.
And that's not uncommon to see things not
Yeah.
perfectly realize the theoretical limits, because there's
Yeah.
and like you said, in this case, there's conduction is one of the dominant sources, so mass probably isn't doing much to fix that.
Yeah, and also in this case, it's the mass of the total wall, so you include the wood studs in that and
That's
things
true,
like that.
yeah.
And so you're not quite doubling the mass, and whatever. So but a 2x4 wood stud wall with the pack rivet clip on it and a single layer of 5/8 Type X drywall on either side usually is in the like STC 54 to 56 range. So it's 20 points higher than that.
Yeah, and that's a very solid improvement for those who are kind of wondering what that's like. I mean, if we did that in your bedroom, for instance, you'd be very happy. It'd be a much quieter bedroom than is typical. If we did it in your theater room or your media room or whatever, it would be a very, very significant increase for a fairly modest cost. Part of me has always wondered why this is not like standard building practice for sensitive rooms, like again, like bedrooms and things like that, just because it would be nice to have in most homes. Whereas what we're stuck dealing with is pretty pitiful. I mean, we're talking about this in terms of like actual solid sealed walls. Now cut a hole and put a hollow core cardboard door in there. Things get a lot worse yet. And that's normal, typical, at least US construction. I know there's people in other countries who are thinking, no, we have concrete and solid core doors. But honestly, in the US, we don't. It's typically honeycomb cardboard core, with fiberboard on the outer parts doors, in lightweight half-inch drywall with 2x4s that are not particularly straight or dense anymore, and it's just the way it is. And so then people complain about how they can hear their kids in the morning, and they watch TV and they can hear it clearly in the other room, and it's like, sorry, it's the way houses are built.
Yep, that's the way houses are built for sure.
Yeah. So going back to all of this, that decoupling, that's a big jump. But then at that point, it's not like you can like add another decoupler and get 20 more points. Like that's kind of it. You're not going to get much more increase. I know there's different isolators, and you sometimes get a couple extra points on some of the more extreme isolators over others, but they're typically within a few points of each other. I mean, I think at this point I've used every clip on the market, from Kinetics, Pack, and Hush Frame are the 3 brands I typically work with, and depending on the levels, they're priced quite differently. The only one that I think performs a lot worse than the others is the clip and hat channel, where the clip has no grommet on it. That one performs a bit worse. And that one's still not terrible, but it performs a bit worse than the rubber grommet ones.
We have those. So our clip with the rubber on it is the Rizik 1. Our clip without rubber is the Rizik V. And on a wall, the Rizik V is not that much worse than the Rizik 1. On a ceiling, there is a much bigger gap. And the Rizik 1 is significantly better performing than the Rizik V on a ceiling. And I'm not entirely sure why, but I have some theories that I'm fairly confident in. But I mean, I would say that like amongst the clips, especially from the ones that are manufacturers that have done a lot of acoustical testing and all this kind of stuff and can really back it up with the data and things like that. And their acoustical performance, you might see some variations of a few points if you're comparing this one to this one. And if they're tested at different labs and those kinds of things, like you would expect some variation. I would say if it's within 5 SDC points and it's nominally the same wall and it's within 5 SDC points, but they're tested at different labs at different times and things like that, you can't say that there's a true difference between them.
Yeah, which is kind of scary. But that's that conversation you said we should have another time, which is that apparently if you take a sample and you pass it around to labs and you ask them all to test it, and you'd expect to get a result that's within a point or two, you're going to be very disappointed.
Yes, and I can talk at length about that because we did that. It's called an interlaboratory study, an ILS or a round robin, and we just did that for, I think we sent samples to 15, 16 labs, and we had them all test two same wall configurations and things like that and pull all the data back. So this is part of ASTM, which is the standards organization that oversees, like the ASTM E90 is the test standard that we use to do an FCC test. And so this is part of that standards organization. And so we did this, I was one of the co-chairs of it, and we did this huge interlaboratory study and collected tons of data. And we're still kind of in the process of going through all of that. But yeah, I can talk about that at length at some point if you and folks are interested.
It's probably worthy of its own show. I'll just say
yes.
on my end, I would love to know why, because I think and this is not unique to this test. There are so many standards tests that I rely on or even do myself where there are distinct, significant differences between tests and environments where there shouldn't be. And to me, if you don't know why, that's like extra bad. Like if you know why, that's one thing, because then you can start to work on it. Like if it's one of those things, people are just not being as careful as they should be, or there's, maybe in the case of this, there's flanking paths that are more significant than people realize. But if it's like one of those, yeah, we don't have a good understanding of why, that gets scary, because then the reliability of the data gets tough. I'm sure, maybe I'm wrong. If I asked you which one of those labs had the right date, like the right answer, could you give an answer to that? Or is it, we're not really sure? Yeah,
no,
I didn't think
there is no right answer, as we know it now. So like, oh yeah, goodness, without getting into all of this, but so yeah, so one of the reasons that we did this interlaboratory study around robin is to start to try to answer that question of why do we have this big variation, and I think I have some reasons and things like that. But there's a lot of things that we don't really know and we're not entirely sure of. But this is like back to your kind of your intro at the beginning where, you mentioned somebody was talking about being like this younger generation of people kind of coming and like
yes.
trying to change a bunch of stuff. So like this is a big part of that, like doing this round robin and trying to change these standards and create higher precision within our test methods. So the SDC test method turned 75 this year. So we've been doing that test roughly the same way. Yes, it's a simple test, and we have, I think, much better ways, like the swept sign that you mentioned, right? We have things like that that are fairly simple to implement, that we can do that are way better. And 75 years ago, when they did this, like
they couldn't do that.
You didn't have the technology to do that. I mean, the way we used to do reverb measurements was you had a pipe organ and you had a dude in a little box in your reverb chamber counting down with the stopwatch. Like, we don't need to do that anymore. But like our standards are still kind of based off of
the same old ways,
really old ways of doing things.
I think one of the things that like gets people is that the old method is so simple. You could literally use a piece of graph paper and a slide rule and do all the calculations you need to figure out that you don't even need a slide rule. Actually, most people could do the math in their head for the isolation. But the newer method that relies on essentially calculating the transfer function of the wall is mathematically more intensive. But the wonderful thing is you and I don't need to do that math. We can write a program that does that math for us.
Yeah, or and AI can write a program for us that does that for us. Like, I mean, we're in a completely different world now. And it's a rapidly changing world too. And so we just have so much more like technology and resources, at our disposal that like we can get a lot more out of it. And the thing with the SDC test is also that we don't get, like as I'm doing product development and things like this, and I'm trying to figure out how to modify a product or create a new product or like modify an assembly to get better acoustical performance out of it. From a typical SDC test, I don't really get enough information to be like, oh, here's the thing that I need to go do to like make this better. And so, we just don't have very fine grained measurements. And so it makes it harder to do good engineering work.
Yeah, for sure. Well, so I was talking to somebody earlier about a project. So they want pretty good isolation, and
Mm-hmm.
not to the extent that we would do cost no object crazy stuff, but they are definitely willing to spend the money it takes to do it right. So the approach we're going to use, which you're familiar with, is basically a clips and channel type approach. Um, well, I'm going to say it's going to be that, or it's in a basement actually. So it's going to be a concrete basement. There's going to be a wall inside of it.
Mm-hmm.
We're probably not going to try to decouple the wall from the basement. Instead, we're going to use clips and channel, which will have the same basic effect.
Yeah.
There's a reason for it. It's just a structural thing.
Okay.
And then the drywall is going to go in. And so what we were just debating was, okay, do we do like plywood and like regular drywall and concrete board and like just layer a bunch of stuff in, which would work. It's just a lot of labor to do it. Or do we just
Yeah.
throw in Quiet Rock? And like in this case, I'm like Quiet Rock 545. It's like the biggest, heaviest, best drywall on the market. It is expensive as can be, but you put one layer up and you're in really good shape. You put two layers up and you're in really, really good shape. Like it's just an easy product to work with. So I said, price wise, we're probably cheaper doing a bunch of layers and you can get the same performance, but we need to check the labor costs because the drywall guys might charge us a freaking fortune to do 3-4 layers of material. And that's the thing. That's like been actually one of my biggest lessons in the industry is that I was so focused on the material costs, I forgot the labor costs.
Yeah. Right.
Labor
That
costs
that
can
is.
quickly eclipse the material costs.
Yeah. So, okay. So to put some more numbers to this, right? So Pack does a lot of testing with Quiet Rock and Pabco. I'm
Right.
good friends with Ben Schaefer, their acoustician. They do a ton of acoustical testing. Like, yeah, awesome
I
folks.
need to tell them they need to make 545 version 2. I don't know what they're going to make different. It's so old at this point. I think we need a version 2 to help sell it.
Okay, I'll let him know. I'll be hanging out with him next week at the ASA conference. So, I'll let him know. Um, but actually, he's the guy that you should reach out to for a conversation too, or like I would jump on here with him. But like just
That
his
would be
knowledge
fun.
of acoustics and testing and stuff like that is yeah, just super sharp guy. I'm just a great guy too. So but so we did a project a while ago. Ben and I and Pac and Fabco did a project a while ago where we were looking at some really high performance walls for some cinema spaces, and this was going to be this cool kind of cinema space where like they were going to have these like tiered, it was like super ultra luxury whatever, and they were going to have these tiered things that kind of, it was a little bit more like an opera house feel where
Mm-hmm.
it was so you have these very steeply raked tiers so that you maintain a closer, a similar distance to the screen and all these kinds of things, right? um and they're each going to be little like pods, like special VIP boxes or something like that. So they were going to have these really tall walls, and so we're trying to figure out how do you get these really tall walls, really good sound isolation and stuff. So we're looking at doing steel walls, but really heavy gauge, like 12 gauge steel studs, these massive studs. um and so we did a whole test series. And so like one of the things that I'll try and do when I go do acoustical testing, and that Ben at Pavco Quiet Rock will also try to do, is we'll go test, like we'll pick a base assembly and then we'll just change one variable at a time, because like that's how you actually learn things, is you go make one
Yeah.
change and you see, oh, what did that do? And then you change another thing, like, oh, what
Well,
did
if you
that
make
do?
5 changes, you have no idea which
Yeah,
of the 5 things you did made a difference.
exactly, right? So like, so this is a oh, and you said I could share my screen. Let me see if, like, should we try
Yeah, at the
that?
bottom there should be something that says present.
Hit
If you click that,
present,
it should give you the option.
share screen,
Yeah.
share screen. Okay. Um, just gonna go entire screen,
And then I
and
need to add it to the stage. Let me do that, and everybody
okay,
should
cool.
see it. There we go.
All right. So you see here, this is this like big crazy. This is a double stud wall. So a lot of times, right, like we'll use double stud walls for isolation, and we'll have these two separate sets of studs. But in
Yep.
this case, because we are going so high, you couldn't get there. You would have to have even bigger studs than these like 8-inch steel studs that we had anyways. So in order to
Yeah.
get these like 60-foot heights, we had to brace them, cross brace them, which then
Yeah.
eliminates your isolation. So then we added the clips for the decoupling on the outside. So we still have some sort of, structural separation here.
Yeah.
So this wall here right in the middle, the STC74, has 3 layers of 5/8 Type C drywall, which was very specifically chosen because a layer of 1/2-inch Type C, sorry, 3 layers of 1/2-inch Type C, each layer weighs about 2 pounds per square foot, so 3 layers is 6 pounds per square foot. Quiet
Which
Rock
is about what the
545,
545 is.
about 6 pounds per square foot. So we're matching the mass. So we've sort of eliminated that weight variable. And then we're looking at just what the Quiet Rock does. So in this case, we just changed out the Quiet Rock on the direct side, and we got 3 points. So it did make a difference. Now, 3 STC points is noticeable, but I would say barely so. So, you know, it made a difference, but then you kind of got to go figure out like what's the price difference between these things, right?
Yep. Which could be a labor thing, or it could be a material. I mean, I think it depends on the area. If you're building a super high isolated theater in a rural Midwest America, construction costs and material costs are both lower there. I know this because I work everywhere in the country. I have to get the product and as a result know the pricing. So if I'm ordering your product, that's different. It comes from a central location. It's the same price kind of everywhere. If I'm ordering Pabco Quiet Rock, that has to come from the local drywall, like a Larson's or something like that. Lawson's, the L&W, one of those types of places. So then, like, I'll call my rep and I'll say, "What's the price in LA?" "Oh, it's $325 a sheet." "What's the price in Iowa?" "Oh, it's $260 a sheet." It's like, what the heck? But it's just different costs, trucking costs, shipping costs.
A lot of it is shipping costs, those kinds of things, depending on where it is and stuff like that, right? And like, so Pabco's a West Coast company. Most of their manufacturing is out on the West Coast, as far as I know. So if you're getting something on the West Coast, it's I mean, depending, if you're in some really expensive market like San Francisco or something, odds are it'll be more expensive there. But generally, if you're West Coast, it might be less expensive than if you're on the East Coast, just because you've got those shipping costs. And for 545, your shipping costs are substantial because the stuff just weighs a ton.
Yeah, and it's not stored locally typically. That's the other negative with it I find.
Correct.
Is that if you are using it a lot, it's not like your local L&W is going to have it in stock. They're probably going to have to bring it in from a larger location or a warehouse somewhere else more central, and so now you're typically
direct from Pabco.
Yeah, and then you get an extra shipping cost for that. Actually, I found out because there's two. I guess there's the to get it to the local location, and then there's the local truck they use to get it to you that has the necessary stuff on it to get it off the truck because it's so heavy they can't just carry it off.
No, they are heavy.
It's some crazy drywall, but it works, as you can see from this. So you mentioned something earlier that I think is worth pointing out. So we have a single number here, and it tells us a lot, especially if you understand what an STC curve looks like, but we don't really know what the transmission loss curve look like. It's possible, for instance, that even though it's only 3 points, that actually it's way more than 3 decibels of improvement at certain frequencies. It just may have had enough errors, for instance, in the calculation that it couldn't go higher than 77 because maybe there's a resonance at a certain frequency or a certain area where it's just not as good at isolating or something like that.
Yeah, right.
So I do wish we got all the data. That we rarely get the actual transmission loss data from manufacturers.
So let's look at 16, 17, and 18. So I can come over here, 16, 17, 18. Go here to my Excel button. And give it a minute. So here's all the data. So here's these walls.
Now we got the raw data.
Yeah, so here's the raw data. So if we go do this, now we get
make a line graph.
Here's our graph.
Awesome. So yeah, you can see. So is the blue the 545 by chance?
So the blue is 545 on both sides. The orange is 545 on one side, the direct side, and then the green is the
similar mass,
3 layers of jip on either side.
Yeah, so that kind of shows what I was getting at, I guess. So it looks like the orange is not really significantly better. It's a little bit better. The blue, below a certain frequency, it's not really any better. Above a certain frequency where that mass is really dominating and maybe some of the coincidence frequency dampening that's been improved is showing that we're getting like way better isolation than just the STC alone. I can't read the numbers on that, but is that like, what, 6+ dB more?
Oh, I mean, so right here at 2500 hertz, which is a coincidence dip for just typical drywall typically, that's 80 for the Quiet Rock 545 on one side, 3 layers of
Is
gyp on
that
the other
100
side,
at the blue?
and that is 98.
98. So it's okay. So it's almost 20. It's 18 dB improvement.
Yeah.
So that's massive. So
Yeah,
that goes
so
to show you where you can get some more value from the 545 that's not reflected in that number.
yeah, so if you
And
just look at these single number ratings, this wall is an STC 76, this one's a 77. So if you're just looking at the single number STC ratings, you're like, oh, well, this one's the best. But if you come back over here and you look at this, you're like, no, this one's better. But also, like, this one's already getting you at these like 80 dB TL, right?
it's a
So
lot of isolation.
if your source level is 100 dB, then on your other side of the wall, it's maybe 20 dB, which
Yeah.
is probably on the noise floor. So
Now, at the low end of this, at those really low frequencies, I think this is the other. So a lot of people are like, I want to contain the bass. And I do think that a lot of rooms, it's pretty easy to get to a point where you've contained enough of the mids and highs that like other factors dominate. In fact, the one that's like the bane of my existence is the doors, because it's really hard to get doors that can come anywhere close to the walls that don't cost, well, they all cost an arm and a leg, but you know, some of them cost a couple people's arms and legs. So at the low end there, though, people get into wanting to contain the bass, and you can see like, it doesn't really matter how much extra mass you put on this. It didn't do anything. Like it didn't add, there's at the really low bass frequencies, there's no more isolation because they're all about the same mass.
Right.
And
they're all the same mass and they're all the same isolation. So the difference in these, and where you see the differences up here at these kind of mid and high frequencies, especially, that's the damping that's in the Quiet Rock 545. That's the constrained layer damping, which is most effective up here in these region. High frequencies, which is the coincidence chip for the coincidence region for the gypsum board.
Yeah, and I think if you were to add some of the other pretty good walls, it'd be interesting to see this. I'm going to guess that you're not going to see huge differences at the really low frequencies, as long as it's still a double stud wall with the same air gap and everything. Because you get to a certain point where like the biggest differences become bigger air gaps, stiffer wall structures. At some point, if you're trying to block a lot of bass, concrete becomes your best friend. And the hard thing there, I actually asked you about this one day because a lot of your data was on aerated concrete, and we don't really use aerated concrete. And I actually went to a lab recently and I said, okay, what would it cost if I wanted to have tested a double concrete wall utilizing, so I don't know if you guys have this, Kinetics has a concrete wall decoupler. So you build your wall on top of a pad, and then at the top, there's like, it's like an L bracket with basically elastomer pads on both sides. And so you have an air gap, call it a 1/4 inch at the very top of the concrete wall. And then it's sort of held in place with these, I'd call it more like a clamp almost, that's decoupled. And I said, what would it cost to test that? And the guy goes, I cannot support a wall that heavy in my lab. And I called another lab. I said, what would it cost to test it? And they said, I can't. Same thing. We cannot support a wall that heavy in the lab. We just don't have it. And so you get to a certain, he also said that wall would have more isolation than his partition wall would. And so that he would not be very certain that the results we're getting are that wall and not his partition wall.
Right. So the other thing here, like, so here's the test report for this, right? So if you look, let's see, this is an older report from theirs. So here, and this is, so this testing was done at North Orbit Acoustical Labs, which is where we do all of our wall testing. And one of the reasons that we do it there is, one, they have very high flinking limits. Also, they're great to work with, and they're super detail oriented. They have really high, like really tight repeatability. If you have them rebuild something, like even many months apart or something like that, and you retest the same wall, you get like very
that's actually
results.
who I was talking to about you.
Oh, Dave Berg.
Yep, Dave. Yep.
Yeah.
I'm planning a trip out there to do some fabric testing. So
okay,
he apparently, like, because this is a side thing and has nothing to do with isolation. We typically do stretch fabric walls over absorbers and diffusers just for looks in theaters, because it looks better than just having a bunch of acoustic treatments bolted to the wall.
Yeah.
And we've been having issues where fairly unpredictably we get more absorption than we expect. And so basically, if you try to account for the absorption that just having fabric over an air gap would give you, and then the fabric directly over an absorber actually shouldn't change the absorber's absorption coefficients at all, we don't get a number that's anywhere near what we're getting in the real world. And so there's all this, call it hidden alpha. There's all this absorption in the room we can't account for. And the answer, we think, and he agrees, is the fabric. It's that when you add a fibrous absorber below it, there's a lot more absorption area than just the, like, you can't just pretend like that fibrous area only accounts for what its square inch range is, because it's actually affecting other parts of the wall surface that are just open to the drywall as well. And so what I said to him was, rather than stick it in an impedance tube, can we actually build a stretch fabric wall in your lab and test it? Basically stretch fabric, no absorbers, then put absorbers in, but not the whole thing. Put, like, we only cover about 20% of the wall with an absorber. So 20%. He said, that's a great idea. That's what everybody should be doing. So
Wait,
now
are you gonna build this on a wall, or are you gonna test it on their
I think we're going to test it
floor
on
in a
the
typical
floor.
C423 test?
Yeah, I think we're going to do it on the floor. I don't really think, I mean, probably the wall is the right way to do it. I just don't think the difference is that great and
Well,
enough to deal with the complexity.
Where are you getting, what frequencies are you getting the higher absorption values at, absorption coefficients at?
It's mostly mid-high frequencies, like
Oh,
above
really? It's mid
200
and high
hertz or so.
frequencies where you're getting
Yeah,
more.
it's not bass. We don't. I
Okay.
mean, I would happily take extra bass absorption. We don't get
Yeah, of
free extra
course.
bass absorption. We get free extra mid. It's like we basically target typically RT 60 times in the range of 300 milliseconds. Smaller rooms maybe 250 milliseconds to like 500 milliseconds for much larger rooms. And we'll
Okay.
design a room. We'll target, I'm just going to make up a number, 400 milliseconds. We'll build the room and it comes in at like 170 milliseconds. Like, we're not even close. And so we've been trying to figure out where it's coming from. And there's rooms that other people design that I test that are way off. There's rooms I've designed where, like, I had one recently that was very close to target, and another one that was designed the same way that was way off target. And
So,
the only difference was the fabric that was used.
These are home theater kind of spaces, right? These are theater spaces. So you've got furniture in it also,
Yeah.
right? That's soft surfaces. Do you
Yeah,
have any
we account for
absorption?
that,
Do you
though, in
have
our
any absorption values for those?
We do, yes. And we even
But
include
how good are those? Because
probably not very good at all. It came from the same kind of stuff you were mentioning earlier. And it would be interesting to say, like, to Dave, can I go to Pottery Barn and have them ship a bunch of couches to your facility and we throw them in the lab and test them? Because the data came from stuff that was done back in like the 50s and 60s, and it was thrown into a report as just, they had like, what is a fabric couch? What is a church pew? What is a church pew filled with people? And then we kind of extrapolated from that for our purposes. But I've never actually seen absorption data for what is a home theater leather chair? What is a home theater chair covered in, I don't know, wool fabric or something that probably has, so all that would be very useful information. But I don't think, so there's a couple rooms I've tested where furniture couldn't be the explanation because the only chair in the room was one leather chair. It wasn't even like a couch or anything. It was just one small leather chair.
Okay.
No.
Yeah, I mean, that is interesting. Well, and I'm glad that you're working with Dave in North Orbit, because they're great folks to do that. Just to shout out one other lab. Whoops, here's my notifications. Riverbank Acoustical Labs, the original acoustics test lab. They're the place where they used to do the reverb measurements, where they had, like, some organ pipes and a guy sitting in a little wooden box, like, measuring it with a stopwatch. That was the beginning of these absorption tests that we're talking about. But Riverbank has started doing
came from there.
Yeah. Yep. Yeah. They have been doing these kind of like novelty tests where they have tested non-commercial things. Because most of the acoustical testing, all this kind of stuff that we're talking about, is usually paid for by manufacturers like PAC, right?
Yeah.
And so Riverbank, I think they did some absorption testing of, I think they did Christmas trees this past Christmas holiday season. They did egg cartons, which you will appreciate that that
It's
reference.
used a lot when it shouldn't.
Yeah. Put a lighter to an egg carton and then decide if that's a good idea to put in your space.
Yeah. That's a whole other conversation we should have, is utilizing what I would call non-official, non-UL rated stuff in your acoustic designs, whether it be isolation and I understand in residence you can do whatever you want, but I still have to question what the insurance company is going to say if your house burns down and they find out you had, I mean, I saw somebody who was putting basically polyurethane foam in their walls, and it was not designed for that. It was just like, packing foam. And I said, I don't know that that's better than the materials that are designed for it, and I don't know how that's going to hold up in a fire.
I mean, I don't know what they're trying to do with it, but if they're trying to do any kind of acoustics absorption, sound absorption with it, it's probably worse than the materials that are typically used for that.
I would
And
think so, but
also
yeah,
not great in a fire.
yeah, that's always my concerns with those. The other one I see is people, there's actually some professional companies that do this too. They have their like proprietary IP for the layers in the wall, but the stuff they're putting in there, it's like linoleum and drywall and like tile, like, bathroom tile. It's just like random stuff. And it's like, I don't know that that's supposed to go into a wall. I don't know what would happen if something
I
happened to that house.
I also don't know that it really does that much
Better
for
things.
you,
Yeah.
right? I mean, like, because
I think they're trying to create chaos with those coincidence frequencies, but I don't know that that's the
it
right
it
fix.
it just I mean, but like to come back and look at this graph, right? Like, so here's the just base drywall, right? And so like yeah, the quiet rock, like having quiet rock on both layers, and there's a reason, and we can kind of go into why, there's a smaller gap here and then this huge gap here. But like down here at these mid and low frequencies, right? That, as you were talking about, are really the issues. Like, we're similar mass, similar stiffness, and we're similar TL values.
Yep.
Um, so you're just not gaining all that much from it. And so, Quiet Rock 545 has a bunch of dissimilar layers in it and things like that. So like up here, if you're trying to do these higher frequencies, like totally it gives you bigger differences. And there's certainly use cases where using Quiet Rock totally makes sense. And if you're trying to get this extra little bit, things like that, like, yeah, it can be a great tool. But I think just all things, people, there's nuances to when and where to use them and things like that. And the things get overly applied, overly extrapolated, and things like that, overly generalized in
Yeah.
terms of like this is, and
When I
that
hear,
goes for
so
Quiet Rock or Clips or whatever it is.
for sure, there's a rationale for using lots of different types of materials, and I get it because they all have different acoustical impedances to them. They have different coincidence frequencies, and so I think the idea is you don't have materials that are overlapping with that. I get that, but like the end result isn't worth the effort, kind of a
I
thing.
I totally agree. And it's also kind of like, you're sort of playing this game of whack-a-mole, right? And so it's like,
Yeah.
okay, so like, we can get, you know, really good high frequency TLs fairly easily, right? With some mass
Yeah.
and some isolation. And those high frequency tails is where your coincidence dip is for typical drywall. So like, even if you have a coincidence dip, but at the bottom of your coincidence dip, you're already at 60, 70 dB for your TL, that's no longer probably the issue. And your issues are more at mid and especially low frequencies. And playing around with all those different things that change your coincidence dip probably doesn't do a whole lot down at low frequencies. And so you're just spending time and money messing with stuff that's not actually making a difference in the area where you really care about it. Um,
Yeah,
and
for sure. And those higher frequencies certainly matter, but like you said, at that point, it's quiet enough. Now, I got one last thing to mention, and then I actually have to cut the show because my wife's got to do her class. She's got to teach. So,
oh, okay,
um,
fair enough.
but it's a good conversation. We should definitely do more of these. So, when I sent you the invite for this, I also sent you something just because I was proud of it. And it was the noise data from a room I did, but it goes to the point we're making because you said to me, "How did you measure that?" And I was like, "Well, I used a trick." Um,
Yes.
And now you've heard of that trick, I assume, after I explained it, or no? Because I know there's
Not
some people in your ASTM group who actually know more about it than I do.
who, because I need to go talk to those people.
Well, maybe
Um,
I'm wrong. You should have people that know more about it than me. I didn't
I
invent
mean,
that idea. I stole it from
no.
B&K.
Oh, okay. Well, so I mean, one, Jim Weir retired and he's no longer showing up at ASTM. So he was the BNK rep, representative
Who would have known those things? Maybe I need to,
at
I'm already part of
BNK.
CDIA. Maybe I need to join ASTM and start bringing the random stuff I've learned. And then you guys can be like, what the heck do you spend your time doing?
You should 100% join ASTM. And it's totally worth doing. The yearly membership cost is not that much. You get to participate in standards development, and we're doing a ton of standards development. We're changing a lot of stuff.
Yeah.
There's a bunch of cool stuff going on.
I have selfish reasons for wanting that because I'd like you guys to adopt some things so I can say, yeah, it's a real standard. I didn't make it up.
Well,
Right now, it
show up
feels that way.
and propose it. Start a working group and start developing it.
Yeah.
And
But okay, so back to the point I was making, you were
yeah,
saying
right.
like 60 dB is already a lot of isolation, and it is, but you do get into some of these extreme rooms, like that one that I sent you the data from, where the sound isolation is actually needs to be and is effectively high enough because we're trying to hit these crazy low noise floors. Now, I would argue, does it really need to be that quiet? No. I mean, I think that room, if you were to try to convert that isolation data to an NCB value, because it's below the actual NCB scale, it's like NCB -6 or something like that. It's like a really low number. So,
Yeah.
you get to a point where it's like silly low, but the idea behind that was to make it so that if you're watching a movie, there's a 0% chance that there's anything like The Quiet Place is a great example where the creatives are playing with silence as part of the effect of the movie. And so the argument is you don't want to be distracted by the sound of your projector or the sound of outdoor noises, the neighbor using the weed whacker or something like that, if you're trying to fully experience this movie as it was intended. I get that this is over the top stuff, but that's the point. Like, these are over the top rooms for people who are willing to pay for that. And the problem you run into, though, and this is true even for testing, is that at a certain point, the quiet becomes so quiet that the electronics are noisier than the quiet. And so it becomes basically impossible to test without using trickery, but there is trickery you can do. In this case, it's a coherent average between two microphones where the room noise is coherent. It's the same between the two mics, and the electronic noise is random. And you can basically get rid of the random noise, keep the coherent noise, and get an accurate measurement of the noise floor, not swamped by electronic noise. You have to know how to do it. But like I said, I don't actually have to know how to do the math. I just have to know that the feature exists in some piece of software for doing that. And this particular technique is actually used for measuring electronics all the time, because modern like op amps and stuff are so quiet that they're quieter than the measurement devices being used to measure them. And you have to basically average out that noise. And the same thing is true here. We're building rooms that are quieter than the microphones we're using to measure them. So we have to average out the mic noise in the same way.
The mic noise. Yeah.
Yeah. So that's what we did in that room, and it worked, as you saw. It's pretty cool. And actually, just to validate, because a lot of people, when I first showed them this, they're like, well, how do you know that's accurate? How do you know it's not like averaging away real noise? And I said, well, okay, first off, technically it couldn't do that. Like, if you understand how the method works, but you know what? Let's prove it. Let's just make ourselves feel better. And interestingly, I had this idea of using a mic calibrator to do that, because the mic, even though the mic calibrator is being used at a distance, it's a constant frequency and a constant noise. And we know what that is. We can calculate what the SPL would be next to it versus a foot from it versus 6 feet from it. And so if I precisely place a, let's say 114 dB calibrator at 1 kilohertz, and then I put the microphones at that distance, and I can measure it then using just a single microphone calibrated. And then we know that's right. And then you can do the 2 microphone method, averaging out the noise. And then you can look at the spectrum. And if the peak noise at 1 kilohertz is the same, which it was, but the noise level around it is different, then we know it's doing what it's supposed to do. It's averaging out noise, but it's keeping the peak, the coherent signal. And so I did that, and it turned out that I didn't know if that was a good idea or not, but PCB did the exact same thing. And they put out a
really?
Yeah.
They did. Okay, I may have. I'll have to go back and look at that. I mean, most of the times I'm not playing in places where I'm trying to measure down that low, or there's just other noise really and things like that. So
well, you might have access to better mics than me too. I know that some of the B&K mics are down into the negative dB range. I can't afford those. So my quietest mic are these 1-inch capsules that are around 8 to 10 dBA, somewhere in that range, self noise. And I like the mic to have about a 10 dB margin to the room to feel totally confident in the noise floor measurement. So that means I need something quieter than that for rooms that are at even NCB 10 level. So using this method gives us that buffer.
Interesting. Yeah, just being in a space that quiet is just kind of eerie, which, I mean, for for those films and things that are using that quiet, like, that is probably the point a lot of times, is that kind of the eeriness of that quiet.
It's supposed to be eerie, yeah.
Yeah, but it's also just so infrequent that we actually get to experience quiet like that.
It's true. Because they're not anechoic rooms, I actually find that the rooms are not all that uncomfortable. So the client that I did this for, who's also a friend and business partner, he and I have spent time just sitting in there talking, and like, it's not an uncomfortable place to be. I was in there by myself for a while, and it wasn't a big deal. Whereas people often report, and I've experienced it too, anechoic chambers are really uncomfortable to be in, especially by Like if you lock somebody in an anechoic chamber, turn the lights off and left, that'd be torturous.
That would be torturous. Yeah.
And so I think that because it's a little bit echoic, it's actually not a bad place to be. Like you actually you can hear your body noises, but not that badly. I've been in environments which were maybe a little quieter, but they also were anechoic, and like you could hear the blood flowing through your ears. Like it was kind of
Yeah.
freaky.
Yeah. I mean, I've experienced that just outdoors on a couple of occasions, just, middle of the night out in the middle of nowhere and things like that, where it's like dead silent and you can just hear like
Just noticing things. Yeah.
blood flowing and things like that. You can just notice really like strange things that you typically don't
Yeah.
hear. But
well, we got to close this down, but I want to thank you so much for coming on the channel. I appreciate it. So hopefully I can get you on again. It was a good conversation, and we can talk about labs, why they're unreliable and how we're going to fix them. We can talk about extreme noise isolation and how difficult it is to test. We can talk about all sorts of probably other topics. I joked with my last guest, we could also talk about brownie recipes, and I'm sure somebody would find that useful. But I want to thank you again. I want to say here, let me let you say your thank you, goodbyes, whatever, and then I'll do my little ending.
Yeah, sure. Well, yeah, I mean, this was great. Thank you so much for having me on. Like, this is like, yeah, I could talk about this stuff for days, and would love to be back and talk more about all kinds of different things. But yeah, I think it's great you're doing this, and really appreciate you having me on.
Thank you. All right. So everybody else, please like and subscribe these videos. So like the video, subscribe to the channel. We got more stuff coming and more guests like Mike coming, and we'll have Mike back. If you have questions for Mike, you can put them down below and I'll pass them on. I hope you guys like these videos. We're going to do more of them, but keep coming back. We got more stuff coming. Thanks, everybody.
Take care.